Hello and welcome. So this talk is about the Seer model in epidemic science. And I will show how to estimate the parameters of this model using the curve of the infected people. I'm François Schmidt from CNRS in France. So I've done this work because it's not directly my field of study. So I was interested in this work during the first lockdown in France, during a few weeks. As you can see in this picture, it was a quite severe lockdown and really nobody everywhere in the street. So it was very boring. And that's why I wanted to know more about the model and our epidemic science. For this, I found different books. Some of them are indicated here about the mathematical epidemiology or epidemic modeling. And now I present the history of it very shortly. So there are different mathematical models that have been developed through history to try to understand how epidemic works. So the first one was Bernoulli for the smallpox, and Ross for the malaria, Lotka from the Lotka-Volterra mathematical framework, and then Kermack and McKendrick that published the paper which is indicated here, which was published in 1927. Here you have the two of them. And in this paper, in fact, they are speaking about, they're proposing a model, and they indicate, in fact, the fact, an interesting fact that, in fact, susceptible individuals are still present in the final population. And they also show a curve, which is shown here, I copied here. It's a curve of the infected people. You can see that it's increasing, reaching a maximum, and then decreasing. And they also propose some equations. These equations are now still used for this very famous model, which is called the Seer model. So what is a Seer model? So Seer means susceptible population, infected population, and recovered population. So the susceptible are just the population which is waiting, which is happy. Infected is the population with just the disease, and recovered is a population that is now recovered and cannot be infected again. And there is also a hypothesis of homogeneity of each subpopulation. And so what is interesting here is that, in fact, you can only go from susceptible population to infected population through infection, and you go from infected population to recovered population from recovery. So this is this can be modeled using a mathematical framework, which is indicated here. So first, the evolution of the S susceptible population. You have a coefficient, which is beta over n. N is the total population, and beta and alpha are fixed parameters. And this coefficient expresses the rate of the infection. And you have a multiplication of S by I, which corresponds to the contact rate between the S and I populations. Then for recovered population, you can see the time evolution of R. Alpha is a parameter, and I is, we have only I on the right because you have proportionality only to the I population for the recovery. And then for the infected population, its time evolution, you have first an increased term, and then you have a decreased term. And all the question is to know what is the balance between this increase and decreased term. So the equation is indicated here on the left with the three differential equations. And you have an example here which is simulated. And what we can see, the red curve is the susceptible population. So first, all the population is susceptible, then it's decreasing, and it's reaching a plateau for a large time. the recovered population is increasing and also reaching a plateau, and the infected population is increasing and then decreasing, and the limit of it is 0. So we can see it's indicated on the right. S is always decreasing, R always increases, and I first increases, then reach a maximum and then decreases. And also we can call the maximum, the limit value of S, we can call it SE. And then we, as I said, we see that I goes to 0 and R goes to N minus SE. So for the initial increase, in fact, we can easily show that it's an exponential increase, and the coefficient of this exponential is gamma, small gamma. And this gamma can be written as beta minus alpha. And we can also introduce the coefficient, which is now, I think, quite famous, which is a reproduction number, which is R naught, and which is the ratio of beta over alpha. So we need R naught larger than 1 to have an epidemic. This means beta larger than alpha. So in fact, the initial increase, the exponential increase, is well known. And this is its rate is small gamma. So my question about when I saw this this model is to know what about the decrease. So I tried to look at the different textbooks, and in fact it's not described in textbooks. So my first question was: is the curve symmetric? It means is the decrease the same as the increase? For this, because it's an exponential law, the best is to represent it in a log plot. So vertically here, we have a logarithmic scale. And so the exponential increase is a straight line, and the slope of this straight line is small gamma. And we can see that the curve is not symmetric in this simulation because we have another curve. And what I show in this work is that the other curve is given by capital gamma, and capital gamma is given by the expression which is written here. So minus beta times SE over N plus alpha. So to just to make to summarize, in fact, we can see that we are here interested in this curve I of t. We have an exponential increase with a small gamma, exponential decrease with a slope capital gamma, and these two exponents, small gamma and capital gamma, are given by expressions which are linked with other parameters. So what I wanted to know is how they compare. First, we can, in fact, find the value of SE, the limit of the susceptible population. For this, we have an implicit equation, which is indicated here. So it means SE over N is the solution of this equation, meaning that it should be the zero of the equation f of x, which is indicated on the left. And we can numerically produce different curves like this and find the zero. And then the zero gives the curve on the right, which is here SE of N versus R naught. So we need, in fact, it's what is called an implicit relation. It means that we don't have the analytical expression of this curve. What we know is that for large R naught values, this reach an asymptotic expression, which is an exponential. But what is interesting here is to know that, in fact, we can find this curve numerically, at least. By knowing this curve numerically, I mean the curve SE of n, we can know the evolution of capital gamma. And from this, we can plot the two of them. So gamma over beta and capital gamma over beta. And they're plotted here versus R naught. And we can see, in fact, several information. First, we have always small gamma larger than capital gamma. Then capital gamma is positive. And also, we can see that capital gamma has a maximum value for R naught equal 2.15. We don't know why analytically, but it's a numerical result. And then it's decreasing. And also, we can, in fact, plot and consider the ratio of these two parameters. So if you look at the ratio, small gamma divided by capital gamma, so the coefficient beta is disappearing when we do this. And this ratio depends only on R naught. It means that if we know this ratio, then we can know the value of R naught. And we have also an asymptotic relation, which is R naught minus 1 when R naught is large. So this ratio is a red curve, which is on the right panel. So from this, in fact, we have an algorithm that can be used to extract all the parameters. So what I mean here is that let's assume that you have a Seer model, which is in the real life. And this Seer model is producing a curve for the infected population, but you don't know the parameters, and you want to know what are the parameters of this. All you need to do to find the parameters is to look at the slopes, small gamma and capital gamma. So the exponential increase and exponential decrease. And if you know them, so it's the first step, then the second step is to compute the ratio. And from the ratio, you can estimate R naught. Third step, you can estimate all the parameters, so the parameter beta and alpha. And then from this, you can also find the maximum value of I, and then you can also know what is the value of n. So this algorithm can be tested. So what we have done here is we are making a different simulation with parameters beta, R naught, and n. And we do as if we don't know these parameters. We just have the curve of I. And from this curve, and using the algorithm that I indicated, so the algorithm which is shown here, so using this algorithm only from the curve I of t, we extract the parameters. So the parameters which are extracted have a little star in this table, and you can compare the parameters with the value we gave in the beginning, and you can see, in fact, that they are very close. So it's a way numerically, in fact, to check with different parameter range that this algorithm is nice to recover, to estimate the different parameters with an error which is on the maximum of 5%. So in summary, it means that the algorithm is working. So since we found the algorithm is working, and we want to try to test it on real data. And for this, we used the data of the French pandemic, the first wave in France. It was in the year 2020, in the spring 2020. And for this, what we use is public data of hospitalized people. And so we have the curve is shown here on the left. It's daily data. So hospitalized people due to the COVID. And on the right, it's the same curve, but it's in log plot. So we can see that we have the initial increase. We have a maximum, and then we have an exponential decrease. We can numerically estimate the two slopes. Small gamma is 0.16 and capital gamma is 0.021. And from this, we can consider the ratio and find the different parameters which are given here. So we find the ratio is 7.7, so R naught is 8.7, and we can find the two parameters beta and alpha, which are given here. And also we can show that the number of people is about 50,000. There is another information, which is the people that are in intensive care units due to COVID. And for this, we also have the daily information. And we also show the plot on the left in in natural coordinate and on the right in log plot. And we see we have, again, the exponential increase, exponential decrease, and the parameters small gamma is 0.16 and capital gamma 0.0346. We compute the ratio, which is 4.62, and this gives R naught equal 5.5. So it's a large, as before, it's a large R naught, but a bit smaller. We can estimate the two parameters beta and alpha, and also the number of people, which is 14,000. So it means that associated to the intensive care unit, there is a global population assumed to be homogeneous, which have 14,000 people. So our conclusion is to say, first, we have an algorithm which works because we tested on numerical data. Then we tried to use this algorithm on real data on two situations. First, the ICU, intensive care unit, and then the hospitalized people. What is very interesting is to find that as for the model, we have the increase exponential and decrease also exponential. So it's really close. And so we can find the different parameters. We can find that the R naught was quite large. So, but the number N is not the total French population, but it's a subpopulation. Of course, it doesn't mean that the epidemic was really following a Seer model. It was just an assumption. Let's say if the epidemic is following the Seer model, then we can try to estimate the parameters with our algorithm. Of course, we know that real life is not so simple. And we also need that the parameters are not changing over time. Of course, they are changing because the politics have different measures to try to limit the epidemic. So all these are of course, strong limitations of the application of this algorithm to the real life. So this work is published in this paper, which is indicated here, which was published early 2022. And to finish, I mention different books of mine, which are in different fields. Thank you very much for your attention.